Hello. So far, we have been talking about integrals that involve very thin, long objects so that we can work only in one dimension. Things get slightly more complicated with objects that have two dimensions, even though they are actually occupying a three-dimensional space. A metallic plate could be an example of that. But I wanted to start with something a little more fun, so let's look at something like a pipe or a hollow cylinder and see how we can work out the mass differential for an object like that. Okay, to continue with this integral building process, I want to discuss today a slightly more complicated object. Specifically, we are going to work on a thin cylindrical shell of total mass m, radius r, we're talking about the cylinder after all, and length h. The important part here is that this object is sort of like a pipe that has a very thin wall and it is hollow on the inside. So you could think that all of the mass on this object is distributed along the wall. Of course, it is a three-dimensional object, but part of what we are going to do is that we are going to consider the object as it looks from different perspectives in order to be able to analyze the mass differential as before. Looking at it from the top, this looks like a hollow, thin hoop because the height h is not taken into consideration. However, the radius is evident here. This is the center of the cylindrical shell. The radius goes like that. But in this case, since it is not a long, thin object, but rather a plain one, I mean, you could make this out of a sheet of metal, for example, then we are not going to talk about linear density, but something called surface density, or density per unit of area. Now, this requires a new symbol, and the symbol that we use is the Greek letter sigma, lowercase sigma, which, well, the density is defined as mass per unit of area in this case. And since we can consider this to be an object that is made up of a rectangle that was bent around in a circle, you could think, well, this is a rectangular object that was just like that, and the height is h, and the length or width of the rectangle is basically the circumference of that circle, so that will be 2 pi times the radius, which means the area is 2 pi radius height. So, since that's the area, this surface density, mass over total area, will be the total mass over 2 pi r h. That's on the one hand. On the other hand, we need to consider an infinitesimal element that in this case it is best to think about in terms of a very thin piece of area that covers the whole length of the cylindrical shell. Looking at it from the top, we're talking about a segment like that. That segment is going to have an infinitesimally small mass dm, but because we're taking a little piece of a given area, then this differential has actually an infinitesimal area dA, and part of our job is to have a formula for that area dA. On the one hand, you know that the length as looked from above, which will be the width of this very thin, very tall rectangle, will be ds. On the other hand, in order to look at this at another scale, you might consider that this could be the appearance of the inside of that wall. Consider this to be like a wall or a curtain, and then the infinitesimal element dA will be an area like that. As I said before, a very thin, very long rectangle. At the infinitesimal level, this can be obtained as the area of a rectangle where the width is an infinitesimal arc ds and the height is h. Therefore, the area dA will be equal to base ds times the height. And since the mass is the infinitesimal dm, then this density can be equivalent to dm over dA, or dm over height times ds. Now, if we keep these two parts of the equation, we are left with total mass over 2 pi rh equal to dm over h ds, or what's the same, dm is equal to mass over 2 pi r ds. Notice that the height h cancels out in this equation, which basically means that in our calculations we are not going to need to know how long the pipe or cylindrical shell is. In this case, if you want an integral of some function that depends on the mass differential dm, then you can substitute the integral of that function times total mass over 2 pi r ds. And just like in the first example for this series, S is an arc that starts out at 0, goes around the whole circular shape, and ends at 2 pi r, which is the circumference, which means that the lower and upper limit of the integral are 0 and 2 pi r. So this can be written as mass over 2 pi r integral of 0 to 2 pi r of the function ds. But there is still another way to look at this, which basically depends on looking at the angle that is created when you have this mass differential. So let me draw it over here because it gives us a better angle. Remember that you're talking about this mass differential as a very long, very thin rectangle of base ds. Now, if you think about a point on the axis of the circular shape, say that this is the axis over here, then this distance will be the radius of the circle. But a very short arc length determines also a very narrow angle, d theta. And from our old relationship, arc equals radius times theta, we derive the infinitesimal of arc is equal to the radius times the infinitesimal of the angle. So you can also think of this integral as having the shape of the function mass over 2 pi r times r d theta. And if your variable is now the angle starts out at 0 and goes around once, which in radians is 2 pi. So the limits are from 0 to 2 pi. The radius cancels out, and so that integral can be thought of as the integral from 0 to 2 pi of the given function mass over 2 pi d theta, or mass over 2 pi integral from 0 to 2 pi of the function d theta. So whichever of these two is convenient is something that you need to determine depending on the function that you are given. That's the way that you convert an infinitesimal of mass into an infinitesimal of area and eventually into an integrable variable. Thank you for your attention.